When normal combustion takes place, the compressed charge in the cylinder is ignited by the spark and burns steadily with a flame speed or flame rate of 60 to 80 feet per second, giving a steady and smooth temperature and pressure rise in the combustion chamber. Maximum pressure will be generated when combustion has been completed, and ideally this should occur when the crank is at 8 to 10 degrees after top dead center, where, because of the ineffective crank angle, the volume of the combustion chamber is still at a minimum. Should maximum pressure conditions arise in advance of this, that is, at or before crankshaft top dead center, the engine would tend to run backwards, which we will not attempt to reproduce. The flame rate can vary slightly. For instance, the mixture will burn faster if it's made richer, or if the pressure in the cylinders increases. An instance of both of these events occurs on takeoff, when it's necessary to increase the mixture strength in order to ensure stable combustion because the engine is producing high power. The action of selecting a rich mixture shortens the time required for combustion. Therefore, a faster flame rate results. Conversely, if the mixture is weakened, perhaps in order to gain a better specific fuel consumption, the ratio of the weight of fuel to air changes, such that there is more air, and therefore nitrogen, per unit weight of fuel. You'll remember that nitrogen is responsible for slowing down the flame rate, and, as a consequence of its increased proportion, a slower flame rate results. The higher that the pressure of the fuel-air mixture can be raised before combustion, the higher will be the pressure of the burning gases. Consequently, the greater will be the power output and thermal efficiency of the engine. The compression pressure is governed by the compression ratio of the engine, and is limited by the tendency of the fuel to detonate or knock. During normal combustion, the flame travels smoothly and steadily through the mixture, as the advancing flame front heats the gases immediately ahead of it, so that they in turn burn. Detonation, on the other hand, occurs after ignition and is unstable combustion. Progressively more and more heat is concentrated in the flame front, which is brought to bear on the remaining unburnt portion of the mixture, termed end gas, and its temperature is raised. In addition, the burnt gases have expanded, so that the end gas is subjected to an increasing pressure. Ultimately, there is sufficient pressure and heat available to bring all the end gas to the point of combustion at the same instant, and it explodes with a rapidity comparable to that of a rifle shot. The flame rate increases to 1,000 feet per second, with a degree of violence which will depend on the amount of end gas that remains. You would be correct in assuming, from what we've just said, that detonation will be encouraged by excessive temperature, pressure, or prolonging the time taken for combustion to take place, or a combination of any of these. We'll now discuss these conditions. Any condition that heats the charge before combustion will aggravate matters in the end gas. Preheating the air before it enters the engine, the use of hot air to overcome carburetor icing, or overcompression in the supercharger or turbocharger may well give rise to excessive charge temperatures. Once burning has started, the process should not be prolonged, because the formation of the peroxides and fulminates which trigger the explosion takes time to occur. Anything which can reduce the time needed to burn the charge also reduces the possibility of detonation occurring. Running conditions can also exacerbate the situation with regard to detonation. For instance, under high power conditions, the pressure in the cylinder can be so great as to encourage the formation of peroxides. To recap then, anything which can reduce the temperature and pressure of combustion, or the time it takes, will be instrumental in reducing, or at the very best, preventing the creation of detonation. So what particular steps can we take to prevent detonation happening? It seems that anything which will reduce either the temperature or pressure of combustion, or the time it takes to occur, will assist in this task. The use of carburetor heat at high throttle settings, say above 85% power, or in high ambient temperatures, will increase the chance of detonation occurring. Therefore, its use in these situations is firmly discouraged. Turbocharging or supercharging will both increase the temperature of the charge before it gets into the cylinders. The use of an intercooler will assist in bringing down the charge temperature. The weaker the mixture selected, the hotter will be the temperature of combustion. Conversely, if the mixture is made richer, it will burn cooler and more quickly, thus providing two ways of combating detonation. Overheated cylinders, the formation of carbon or coke in the cylinder head, like the one shown here, which will prevent heat dissipation, will both assist in bringing the temperature of combustion up to the point where it will generate detonation. Running engines at the optimum cylinder head temperature, and ensuring that regular maintenance prevents the formation of carbon deposits inside the engine, are sure methods of minimizing the occurrence of detonation. If possible, the flame should be started from the vicinity of some hot spot, such as the exhaust valve, so that the end gas is pushed away from the hottest parts of the combustion chamber and compressed into a cooler part. One way of reducing the time taken for the flame front to travel across the combustion chamber is to initiate the flame simultaneously from two spark plugs. Certain running conditions can also assist in delaying the onset of detonation. For example, the same power may be obtained at a higher engine speed by using a finer propeller pitch. This enables a smaller throttle opening to be used, which helps in two ways. The smaller throttle opening reduces the cylinder pressure, and the higher running speed cuts down the time available for detonation to develop. A third way of reducing the time it takes for the flame to travel across the combustion chamber is to design the combustion chamber and the inlet ports in such a way as to cause turbulence to occur within the incoming mixture. This will have the effect of accelerating the flame front. We've already stated that the ignition is timed to ensure that all combustion will have been completed by the time the crankshaft has rotated about 8 to 10 degrees into the power stroke. Advancing the ignition timing, in other words igniting the mixture too early, will cause cylinder pressures to rise too rapidly, generating peroxides and fulminates, and thus detonation will occur. Maintaining the correct ignition timing will thus help to prevent detonation, by maintaining the combustion pressure at a level which will not produce the ingredients of detonation. It's important that the recommended octane rating of the fuel for a particular engine is used. If a fuel with an octane rating lower than that which is recommended is used, it will promote detonation, especially under high power conditions. The explosion of the end gas can cause the piston crown to burn, and eventually to collapse. Overheating of the combustion chamber can also occur. This picture shows a piston which has been severely damaged by detonation. The piston crown has been burnt, and eventually it's disintegrated. Detonation may cause the valves to split and distort. It can also possibly burn the sparking plug electrodes. The damage shown here is consistent with being caused by detonation. There is also a sudden rise in pressure as detonation occurs, which applies a shock loading to the engine component parts, which may cause mechanical damage, particularly to the big end bearings and even the connecting rod, although the case shown here is extreme. Finally, because the maximum pressure is generated before the piston is in the correct position to utilize it, the piston has to overcome a high back pressure, and power is lost. The fact that detonation is occurring can be recognized by a metallic knocking sound, sometimes called pinking, which is caused by the violent vibrating pressure waves striking the walls of the combustion chamber.